this time, as soon as you have something that I should look at, then I'll come around and I'll just check it off. I don't want to collect them. I hope we're getting more confident in that answer to the question. Yeah, okay. But did you write it up looking at the notes?
I just put this over the top.
Okay. Okay, so you already have it. Cool. So, the threshold you want is you want little n to be big, so it needs to be bigger than the cutoff. And you want an to be close to. Hold back up. Nope, can't go to the next. You have almost everything. So what are you saying that there exists? So there exists some subsets of how close it is to the between. So you need a sub n to be that close to that. So I'm not happy there. Because right, it's always at least zero. But this doesn't happen for all. This happens once n is big enough. So there exists some sense of big enough. Such that once little n is big enough. Yes. So notice you have an epsilon back here. Yes. So you better declare that epsilon is small. So what's the job of that epsilon? Yeah. So it's like the up or down of the distance to the actual limit. And something bigger than 0. And in fact, like, so this epsilon needs to be declared wrong. And so does the beta. That's what it's. Okay. So, well, what epsilon and beta does all that happen? The limit only shows up. Let's put it down. So, let's put down the definition of the limit. So remember the idea of the limit, and this is like a generic definition now that you can port over to any place where you can make these ones make sense. An converges to L if, no matter how close you want a sub n to be to L, there's some threshold so that once little n is past that threshold, an is that close to the limit. And so how do we measure distance? We measure distance by that. So that needs to get really small. So there's like the inequality that measures the limit. And now it's just a matter of putting the quantifiers in. Well, what epsilon should that happen? It should happen no matter how small epsilon is. No matter how small you want an minus L to be, you can get it to be that small. Well, what little n does that happen? It happens as long as that little n is big enough. And how do you measure big enough? Well, there exists some threshold value such that once little n is bigger than that threshold. Nice. Cool. I will ask this question again on Friday. Cool. So, let's start in on an application of monotone convergence. So what have we shown so far? We've shown that if a sequence is monotone and bounded, then it converges. If it's increasing, then it converges to the supremum of the terms. If it's decreasing, it converges to the infimum. And those things exist by completeness. Here's a nice application of this. Let's prove the comparison test for convergence of series. So I guess to do that, we better start by talking about what a series is. So, object of the poem, the sum from k equals 1 to infinity, is called a series, and now we'll make the formal definition. So let's consider a sequence, ak. So now k I'm using as the indexing variable for the sequence instead of n. Doesn't matter what you call the variable, it could be anything. I'll use it because n is going to have a different job in a moment. The sequence of partial sums for the series is defined by the rule that Sn is the sum of all the ai's starting at 1 going up through On. In summation notation, that's the sum from k equals 1 to n of ak, but this is all very familiar notation, right? So like S1 is just A1, S1 is A1 plus A2, S3 is A1 plus A2 plus A3, and if you want to go any farther than that, you use summation notation so you don't have to write as much. So, there is a sequence of partial sums. I will use this word an awful lot today. What should it mean to say that the series from k equals 1 to infinity converges to a number in terms of this sequence? Because I can't actually add up infinitely many things all at once. Well, it should mean that once the parameter big N is really big, the partial sum is really close to L. Right? Well, that sounds like a limit to me. So the series converges to a number L, and we will write that if the sequence of partial sums converges to L. That seems sensible enough? The series converges if and only if the sequence of partial sums converges. So that's handy. That connects series back to sequences. Everything you know about sequences is also a fact about series. You just have to figure out how to parse it out. What do you think it should mean to say that a series diverges? So a series, well, what does diverges mean usually? That's one type of divergence. You can also have -1 to the n diverges too, right? So the series diverges just means it fails to converge. So that should mean that the sequence of partial sums just fails to converge. So when you say that a series diverges, you're just saying that the sequence of partial sums diverges. Now we'll put the to infinity. An infinite series diverges to plus or minus infinity. What should that mean in terms of the sequence of partial sums? I mean, we're just making up a definition, so it could be anything. I want something that seems sensible. So convergence means that the sequence of partial sums converges. Divergence means the sequence of partial sums diverges. Diverges to infinity should mean the sequence of partial sums does the thing. Yeah. So in general, when you say basically anything about a series, the most obvious definition is the sequence of partial sums does the thing. Nothing deep there. And another thing we can do that's not very deep is everything we know about sequences we can translate to something about series. And that's what we'll be doing today. There will in fact be no epsilons or big N's showing up today, I don't think. Instead, we'll be using the fact that we have all of these properties about limits of sequences. Every one of those facts gives us something about series. Here's one. Let's let the sum of let's let the series from k equals 1 to infinity of ak converge to a. The series from k equals 1 to infinity of bk converge to b. Let's let c be a real number. Then the series from k equals 1 to infinity of the sum converges to a plus b. Does that seem like a fair thing that should happen? Yeah. And if you multiply all the terms in the series by c, then the infinite sum should just get multiplied by that number c. That seem fair enough? But of course we now have formal statements for all these things, so they need proofs. The proof of both of them is going to be basically the same. Let's figure out what this proof is. I'll prove the thing for ak plus bk. So it's simply just unraveling all the definitions. That's the sum of ak, that's an ak be a sequence and bk be a sequence. Let's assume that the infinite series associated with ak converges to a, infinite series associated with bk converges to b. Everything inside is about sequences of partial sums though, right? So those series results say things about sequences of partial sums. So let's let Sn and Tn be the sequences of partial sums for the two things. That seem like a sensible thing to do? And let us actually translate to the definition. So let's let Sn be the sum k equals 1 to infinity ak. Nope, n. So let Sn be the sum from k equals 1 to n of ak. Tn be the same thing but for bk. So there are the sequences of partial sums for this series. So, what can you tell me about the limit of Sn? So what do I know about the sum from k equals 1 to infinity of ak right now? It goes to a. And remember that we have a definition for that. A series goes to a number if the sequence of partial sums goes to that same number. That's the definition. So what can you tell me about the limit of Sn? Converges to a. Excellent. Yeah. And there's nothing deep there. It's just the definition. What about Tn? All right. So now I've unraveled all of the definitions. And let's think about what I want to show. So this will be not part of the proof, this will be in the margin. I want to show that the sum of ak plus bk, k equals 1 to infinity, is a plus b. So in order to show that, what I need to show is that the sequence of partial sums for that series converges. Right, that's the definition. So it sure looks like I want to set something to be that sequence of partial sums. It doesn't matter what you call it. I'm using Rn because well, I guess it's not even alphabetic. St then R. It's close enough to alphabetic. Let's let Rn be the sum from k equals 1 to n of ak plus bk. It sure looks like I then want to show Rn converges to a plus b. Does that feel right in terms of the definitions? So let's now just try to do it. So let's let Rn be the sum from k equals 1 to n of ak plus bk. That is now the sequence of partial sums for the infinite sum. If I want to show that the infinite series is a plus b, where do I need to show that Rn converges? Now I'm just being too quiet.
Say that again?
Yeah. So Rn is the sequence of partial sums for that infinite series. I need to show that Rn converges to something to complete this proof. Yeah.
A plus B.
Yes, good. You don't need to raise your hand for that. I'll make you raise your hand if the class gets too rowdy, but that hasn't been an issue so far. Thank you. Right, I can never gauge whether the answers just seem so obvious people don't want to answer them, or if they're actually lost and just silence is sometimes scary to people for that reason. But we're happy? We feel good? Nice. Does that seem like it should actually be pretty straightforward to do? Yeah, because now we have a finite sum. Rn is the sum of just the AKs plus the BKs. Well, since that's now a finite sum, could I just put all the AKs together? Yeah, so maybe we'll do that. Well, maybe I'll use everything. I'm using associativity and commutativity. Right, there it is now, just with the dots. Let's gather together all the ANs, AIs, AKs. Oh, cool. So that's just the same as the sum of all the AKs plus the sum of all of the BKs. All right. Neato. Feeling good so far? There's stuff that's going to happen on the next page. Yeah. So let's put that here. So Rn is now the sum of just the AKs plus the sum of just the BKs. I have a name for the sum of the AKs. What's the name for that? It's on the previous page, so I need you to remind me. Oh, that's the name for the limit. Sm. And the same thing for the BKs?
Yeah.
I know those limits. Ooh. So this is why I didn't need to have any epsilons or big N's in the proof. I have a formula for the limit of a sum. Cool. That seemed pretty all right. So there were no deep ideas. The only thing that made this proof even a little bit long is the fact that you had to take the effort to translate back to what you want to show. Once you do that, then you can mess around a little bit, use associativity, use limit laws for sequences, and you're done. So we've just proven that the sequence of partial sums converges to a plus b. So the actual limit of the series is a plus b. Cool. All right. So it turns out, and maybe you'll remember getting this feeling when you took Calc 2, there aren't actually that many infinite series that you can compute on the nose. In fact, for most of them, well, here's actually an advantage of thinking about sequences and series. They let you come up with formulas that you can understand, that express numbers that are interesting but that you don't have a name for. Right, like before you write down the limit of 1 plus 1 over n all the way to the n, you don't have a sense for what e should mean. That's how you make up this number. Series let you do exactly that same thing. There are very few series that you can actually compute directly, and it's actually kind of disappointing when you can. It tells you that this series doesn't tell you something new. There are basically two examples of series that I know how to compute. The first is geometric series. If you have any number p in the real numbers, then the sum from k equals 0 to infinity of p to the k is 1 over 1 minus p. That fact look familiar enough? You see it written down? Yeah, that's the one that you learn in Calc 2, and maybe even prove in Calc 2. Homework though, prove that claim. If p is bigger than or equal to 1, then the series diverges. Cool. The next result is the telescoping series theorem. The theorem about telescoping series. Let's try to figure out where this series should converge. The thing that was actually in the notes is wrong. And it's wrong for like a silly reason. But let's figure out where the series should converge by just like writing out the first couple terms. So let's figure out what should go there, and let's do this as follows. Let's let Sn be the sequence of partial sums, k equals 1 to n, of q, k plus 1, minus qk. Because right, there's the thing whose limit I need to compute. So let's just write down the first couple terms. So with that formula, what's S1?
Q2 minus Q1.
Good. S2. Well, I guess it's like slightly annoying. Q3 minus Q2 plus Q2 minus Q1. Anything cancel? S3 is Q4 minus Q3 plus Q3 minus Q2 plus Q2 minus Q1. Same thing? Q3's cancel. Q2's cancel. Ooh, do you notice a pattern? Let's make a conjecture. What do you think Sn simplifies to in general? So let's see, S1 was Q2 minus Q1. S2 was Q3 minus Q1. S3 was Q4 minus Q1. What do you think S5 will be? Yeah.
Q n plus 1 minus Q1.
Yeah. Cool. All right, so this is all like scratch work to even figure out what this theorem should be. This theorem is about like the limit, right? So let's take the limit as n goes to infinity and see what this says. If Qn is a sequence what converges to 0, what can you tell me about Qn plus 1 in the limit? Goes to 0? Oh, so it shouldn't be Q1 which was there. What is this actual limit equal to? Negative Q1? So there's the other limit you know how to compute. You can compute the limit of a telescoping series. And it's called a telescoping series because it has this property that you can write down this big long sum, and then all the terms cancel out and you're just left with the first and the last term. It telescopes. Like how you take a telescope and collapse it. In fact, based on what's written, people think they could write down the proof of this claim now? Yeah, you translate to the definition. Then you'd say, oh, I want to show that this thing converges to minus Q1. Oh, and then maybe you need some inductive proof to do the stuff we did off to the side. And then you take the limit. That's one of the homeworks. Oh, I'm actually plugging along pretty quick. We might have time to think about the homeworks collectively. So, all of that's just like standard results about series. If you add together things, you can compute the limit of the series. If you multiply the terms of a series by a constant, you can still compute the limit of the series. Multiplying the terms of a series together isn't so helpful because you can't like split that up as the sum of the product of the sum. Right? You would have to like use the distributive law, which would make the sum really big. There's something like that you can do. That's there is like a summation by Peretz rule that we certainly won't hit in this class. We could, we won't. But here's like the standard result that lets you prove that new series converge given that other series converge. The comparison test. And maybe even just, I'll say it and like read through it. Fill in the various conclusions. So let's let AN and BN be sequences. Let's assume that for every natural number n, AN is non-negative and AN is less than or equal to BN. Then the comparison test from Calc 2 lets you say that if one thing converges, then so does the other thing. And you tell me. So maybe the takeaway from Calc 2 was that if the bigger thing converges, then so does the smaller. Okay, cool. Let's put that in the blanks. So if blank converges, then blank converges. Which things should go in those blanks? Yeah, I'm going to replace that n with a k though. No, don't apologize. That is like an issue that I make constantly, right? Like the k that's there should be the same as the k that's there. It's really easy to screw that up. And then conversely, if the smaller thing diverges, then so does the bigger. I don't know. Like in Calc 2, you went and used these results to show that like once you have one series that converges, and you have another series that like behaves similarly to this series, then you can show that that new series converges or diverges. And like that's a super intuitive argument that yeah, if it's less than something that doesn't go to infinity, it can't go to infinity, so it's got to converge. And the intuitive reason for that is just monotone convergence. Let's use monotone convergence to do this, and it'll actually be pretty quick. So, oh, I guess here's one note. Claims 1 and 2 are actually the same claim. They're just related by the contrapositive of each other. So let's just convince ourselves of that. If this converges, then that converges. So that means that if this didn't converge, that couldn't have converged. Oh yeah, that's item 2. So I don't need to prove both. They're both the same statement. They're related by just like some logical jiggery-pokery. All right, so let's prove this claim. Let's let AN and BN be sequences. Let's assume that for all n 0 less than or equal to AN less than or equal to BN. Which one do I get to assume converges? Oh yeah, I was just going to write BN, which would have been wrong. That shows how easy it is to make that error. So, since that series converges, that means the related sequence of partial sums converges. So let's let Tn be that sequence of partial sums. So what am I going to put in that next blank? So I know the infinite series associated with BK converges. So that means, yeah.
AK?
I think I want BKs. So I know that the sum of BKs converges, so the sequence of partial sums converges. So there's like the things we get to assume. So this is like the givens. I don't think that apostrophe is appropriate. I think it's wrong. That's okay. So there are the things you just get to know. Now let's try to unravel what we want to show. We want to show the sum of the AKs converges. And let's try to parse that out. What would it mean? What does it mean for the infinite series to converge? have a definition at the start of this packet, right? What does that definition say? There's the thing I want to converge. Means that the sequence of partial sums needs to converge. So I want to show that the sequence given by the sum from k equals 1 to n of ak converges. I want to show that that converges. I don't know what the limit is. I have no idea what the limit is. So I can't compose like some direct epsilon n proof. I need to do something fancy. And right now the only fancy tool that we have is monotone convergence. So if I want to show that that sucker converges, what two things do I need to show to conclude that? If I want to use monotone convergence. What does the monotone convergence theorem say? Look back and remind yourself if you need to. It says that if the sequence is block and it's blocked, then it converges. What are those two things? There's the monotone convergence theorem. Or there's the second statement later on in the same section. Let AN be a bounded monotone sequence, then AN converges. So if I can show that a sequence is monotone and bounded, then it converges. The statement later on says that if I know it's increasing and just bounded above, then it converges. If it's decreasing and bounded below, then it converges. So, with that in mind, I would like to show that this sequence converges. So to do that, I need to show that the sequence is monotone and bounded. That seem fair enough? Yeah. So, let's decide between whether, so monotone means either increasing or decreasing. Let's decide which one we want to show first. So, in order to track, let's remember, S1 is just A1, S2 is A1 plus A2, S3 is A1 plus A2 plus A3. Which way should that inequality go? Which one of those two is bigger? S2. So for that to be the case, I guess A2 has to be positive. Is that an assumption in this theorem? Yeah, I guess bigger than or equal to 0, but that's good enough to get us that, which is all monotone convergence needs. Does it keep on getting bigger when I add another term? Nice. So it looks like I, in fact, want to show it's increasing, which means I'm good enough with showing it's bounded above. So now we have like a really explicit version of what we want to show. I want to use monotone convergence here. We need to explain why Sn is increasing and why it's bounded above. And I think you already know why it's increasing, right? increasing because the individual terms are non-negative. So let's try to do that. So let's explain why Sn is an increasing sequence. And I might even propose, we're doing okay for time. Do you think you could sketch a proof that this sequence is increasing on your own right now? You guys have a little bit of poker faces, so I'm just going to ask this directly. Like, the options are I be quiet for a bit and you do, or I should keep talking. People want me to keep talking. Okay. Okay, well. Those of you who want to like walk it out on your own, it's a super direct proof. Let's try to walk out what we need to prove by just like recalling the definition of what increasing means. And maybe instead let's use not the original definition, but the one that has like a k and a k plus 1 in it. So if I want to show Sn is increasing, what is it that I want to show? And there are two correct answers here, but there's one that will be easier than the other one.
Could you say something like, AK plus 1 is greater than AK?
Yeah, but replace those A's with S's. So we want to show, and I'm going to leave myself a space because there's going to be like a quantifier right here. Sk plus 1 is bigger than or equal to Sk. And I need to show that is true for every k in the natural numbers. And it doesn't matter what we call it. K is like supposed to be the parameter inside of the series. So I think I'm going to replace that k with an n, because otherwise I will get myself confused. And it doesn't matter what you call the parameter, right? It can be anything you want. So, I need to prove a universally quantified statement. So let's focus on this. We'll put it into wants like on the lines in a moment. Why should Sn be plus 1 be bigger than or equal to Sn? Convince me of that. Yeah.
Because that's estimate is the sum of A and K or A equal 1, and then estimate plus 1 is the base of K. Plus it'd be like it'd be equal to it would be equal to S sub n plus a sub n plus 1.
I think that's right. But like, let's put the thing in the space that's going to go before that. I think that's true. So Sn plus 1 is the sum from k equals 1 to n plus 1. So I could split that off as the sum from k equals 1 to n of ak plus ak plus 1. Oh, I'm off page. Yeah, that seems pretty compelling now, right? So because this is positive, when I add something to something, it's bigger than it used to be. So I think there's the proof. Let's just put it up here. And since most of the walk involved Sn, I think we start with this, like expanding this out. So let's see, by definition, Sn is the sum from k equals 1 to n plus 1. Oop, I want n plus 1. Of ak
Ooh, but I could pull out that last term. That's the same as the sum from k equals 1 to n of ak plus a n plus 1. Full stop.
So far, so good? I think that's basically writing down what you just told me to write down. And then the logic was because that thing is positive, if I erase that bit, then the whole sum gets a little bit smaller. So since a n plus 1 is bigger than or equal to 0, Sn is bigger than or equal, Sn plus 1 is bigger than or equal to sum from k equals 1 to n of ak plus 0. So just replace the an plus 1 by 0. Oh, but hey, that's exactly Sn. Thus, Sn is increasing. Cool. That proof feel pretty okay? Does it feel bad in any ways? So maybe people are noticing also that writing all of these summation signs and being very careful with putting the from k equals 1 to n results in taking up some extra space, and it's easy to accidentally lose that. This is a good argument to typeset the homeworks that have to do with series, because then you can use copy and paste, and you won't forget them. And they get formatted better on their own. Cool, so we have that this thing is increasing. What's the thing we still need to show? We need it to be bounded above. So we need to get an upper bound. And there's one obvious pseudo upper bound, right? Tn is probably at least as big as Sn, because Tn comes from adding up a bunch of things that are bigger than the things you added up to get Sn. That's a lot of silly words to say. AKs are less than BKs. If you add up AKs, you get something less than when you add up BKs. And I don't know, maybe it makes sense to do that inductively. I think that's the best way to rigorously do that. So let's use induction. When n equals 1, well, S1 is then just A1 is less than or equal to B1 is equal to T1. So the claim is true when n equals 1. I think I haven't given myself enough space to be as verbose as I seem to want to be. Let's do the inductive step. So to do the inductive step, we will fix some natural number n, and we will assume Sn less than or equal to Tn. We need to show that the same is true for Sn plus 1. Then, Sn plus 1, by this same trick we used down here, is equal to Sn plus An plus 1. I want to show that it's less than or equal to some stuff. What can you tell me about that? How does Sn compare with something? Yeah, by the inductive assumption. Tn plus An plus 1. What else? else do I know?
That AN plus 1 plus BN plus 1.
Good.
And what's all that equal to?
Nice. And maybe we can put like a closing sentence then by the inductive assumption. And that's basically good enough.
I don't have space to go on. Cool. So, Sn is bounded above by Tn, but Tn isn't a constant, so this doesn't count as bounded above yet. I need it to be bounded above by a number, not another sequence. I know that Tn converges, every convergent sequence is bounded. Right, we proved that a while ago. Let's let U be an upper bound on Tn. I claim that U is also an upper bound on Sn, and let's show why. So I know that for any n, Sn is less than or equal to Tn. What else do I know? Yeah, or equal to. Oh, cool. Does that give me an upper bound?
So U is an upper bound on Sn.
All right, so that was all the hard work. Let's just make the conclusion. So, by the monotone convergence theorem, what can you conclude?
Well, let's put the since.
So what two things did we directly show about Sn?
Since it's increasing and bounded above.
And so what does the monotone convergence theorem let me conclude?
And let's just keep on wrapping it up. Since Sn converges, the infinite series converges. So the sum from k equals 1 to infinity of ak converges.
Cool. And all the stuff that's put off to the side is like exploring what it is that we needed to prove to do the proof. It's not part of the proof. Cool. How did that feel? So whenever you want to prove something converges by the monotone convergence theorem, you need to prove that it's increasing. That might be easy or it might be difficult. You need to prove that it's bounded. Might be easy, might be difficult. Once you have those two devices, then you can just say, by the monotone convergence theorem, since it is increasing or decreasing, whichever you proved, and bounded above or below, whichever you proved, you know that it converges. And then in the case of series, you need to add this extra sentence about, so that means the series converges. So let me show you the homework because there's the same typo that needs fixing.
So the first result is the telescoping series. So let's define a sequence by the rule an equals qn minus qn plus 1. Qn minus qn plus 1. In order to make that agree with what's in the notes, that's going to be qn plus 1 minus qn. Then the finite sum you will show is equal to qn plus 1 minus qn. And we just checked that really that statement for the telescoping series converges to minus q. So you'll prove that, and then the next result is going to be you combining the results from this section, including the comparison test, to show that the sum of 1 over k squared converges by addressing those bullet points one at a time. Cool. All right. So, that being done, I think I'm at time, right? Anyone want to come by my office hour today? You don't have to give me a warning in advance. That's cool. Because I also have the Mulligan version of that benchmark ready to go when